Imagine you have 5 cache servers handling millions of requests per second. You're using a simple hash. Take the request key, mod it by 5, and route to that server. It works perfectly, until you need to add a 6th server. Suddenly, modulo 6 gives different results for almost every key. 80% of your cache is now invalid. Every one of those keys hits your database simultaneously, the thundering herd. Your database melts. This is the exact problem that consistent hashing solves. It's the algorithm behind every major distributed system, from Amazon DynamoDB to Akamai CDN to Apache Cassandra. And in this video, I'll show you exactly how it works. Let's start with why naive hashing breaks. With modular hashing, you compute hash of key modulo n, where n is the number of servers. Key user 123 might hash to server 2. This works until n changes. Add one server, and the formula gives a completely different answer for nearly every key. Remove one server, same problem. The math is brutal. When you go from n to n plus 1 servers, on average, n over n plus 1 of all keys get remapped. That's 83% of keys moving when you scale from 5 to 6 servers. In a system handling millions of requests, this means millions of cache misses hitting your database at the same instant. Here's the core idea of consistent hashing. Instead of a modulo operation, we place everything on a ring. Picture a circle numbered from 0 to 360 degrees, or more precisely, from 0 to 2 to the power of 32. We hash each server's name or IP onto this ring, so each server lands at a specific position. Then when a key arrives, we hash the key onto the same ring and walk clockwise until we find the nearest server. That server owns the key. This is the fundamental insight. Keys and servers share the same hash space, and proximity determines ownership. Now here's why this is brilliant. When you add a new server, it lands at one point on the ring. Only the keys between this new server and the previous server counterclockwise get remapped. Everything else stays exactly where it was. The math changes dramatically. Instead of 83% of keys moving, only k over n keys move, where k is the total number of keys and n is the number of servers. Add a 6th server to 5, only about 17% of keys move, instead of 83%. Remove a server, its keys flow clockwise to the next server. The rest of the system is completely unaffected. This is minimal disruption, the defining property of consistent hashing. But there's a problem with basic consistent hashing. If you only place each server at one point on the ring, you'll get uneven distribution. Some servers might end up close together, handling very few keys, while others get a huge arc of the ring. This is especially bad with small numbers of servers. The solution is virtual nodes. Instead of placing each server at one position, you place it at many positions, typically 100 to 200 virtual nodes per physical server. Server A becomes A1, A2, A3, all the way to A150, each hashed to different ring positions. Now the ring has hundreds of evenly spread points, and each physical server handles many small arcs instead of one potentially huge arc. The distribution becomes nearly uniform. Virtual nodes also solve the hotspot problem when a server goes down. Without virtual nodes, if server B fails, all its keys go to the single next server clockwise, doubling that server's load instantly. With virtual nodes, server B's 150 positions are scattered around the ring, so its keys distribute evenly across many other servers. The load increase is spread proportionally. This is why every production implementation uses virtual nodes. The number of virtual nodes per server can also be weighted. Give a more powerful machine 300 virtual nodes and a smaller one 100. The ring naturally routes more traffic to the stronger server. Let me walk through a concrete example. Say we have 3 servers, A, B, and C, each with 4 virtual nodes for simplicity. We hash A, 1 through A4, B, 1 through B, 4, and C, 1 through C, 4 onto the ring. That gives us 12 positions. Now a request comes in for key, user, 42. We hash, user, 42. It lands at position 78 on the ring. We walk clockwise and hit B, 3 at position 91. So the request goes to physical server B. Now we add server D with 4 virtual nodes. D, 1 through D, 4 land at positions 45, 120, 200, and 310. Only keys that fall between these new positions and the previous server counterclockwise get reassigned to D. The majority of keys remain on their existing servers. Lookups remain O of log n using binary search on the sorted ring positions, whereas consistent hashing used in practice everywhere in distributed systems. Amazon DynamoDB uses it to partition data across storage nodes. Apache Cassandra uses it as its primary data distribution mechanism. Each node owns a token range on the ring. Akamai's content delivery network uses it to route requests to edge servers. Memcached and Redis clusters use it for cache distribution. Discord uses it to route users to the correct WebSocket server. Load balancers use it for sticky sessions. The same client always hits the same backend. Anywhere you need to distribute data or traffic across a dynamic set of servers, consistent hashing is likely the answer. Let's compare consistent hashing to the alternatives. Modular hashing, hashmod-n, is simple but catastrophic on resize. Range-based partitioning divides key space into fixed ranges assigned to servers, but requires manual rebalancing. Rendezvous hashing, also called highest random weight, computes a score for each key server pair and picks the highest. It has similar properties to consistent hashing but requires evaluating every server for every key, making it O of n per lookup versus O of log n for consistent hashing. Consistent hashing wins in practice because it combines minimal data movement, even distribution with virtual nodes, O of log n lookups, and simple implementation. To summarize, consistent hashing solves the fundamental problem of distributing data across a changing set of servers with minimal disruption. The core idea is simple. Put everything on a ring, walk clockwise to find the owner. Virtual nodes ensure even distribution and graceful failure handling. When servers join or leave, only a small fraction of keys move. It's O of log n for lookups, simple to implement, and battle-tested in every major distributed system. If you're building anything that distributes data or traffic across multiple servers, consistent hashing is the algorithm you need to know.